Hi, I'm Alan Cudmore from NASA Goddard Space Flight Center, and today I'm going to give you an update on the high-performance spaceflight computing middleware project. During this presentation, I'll provide an overview of middleware, a look at our upcoming Middleware Release 4 features and plan, the Middleware Release 4 hardware environment, and finally, we'll take a look at some of the post-Release 4 research topics we've been working on as part of this project. I've reported on the HPSC middleware 2 times before, but for those that are not familiar with it, let's start with a brief overview. But before we get into the project itself, I would like to acknowledge the team that works on HPSC middleware. We have team members from JPL, including John, Dennis, Rob, Brent, and Joe. And at Goddard Space Flight Center, our team consists of myself, Sergio, and Jonathan Wilmot. Now let's get into the overview. For the sake of brevity, I'm just going to call HPSC middleware. The middleware is a joint project between NASA Jet Propulsion Laboratory and NASA Goddard Space Flight Center. Middleware is funded by the Air Force Research Lab, and we are grateful for the opportunity to pursue this research. Middleware was originally targeted to run on the high-performance spaceflight computing chiplet, but given delays in the hardware, the middleware is targeting a more generic multi-core system-on-chip, or SoC, systems, such as the Xilinx UltraScale MPSoC. The objectives of the middleware include provide applications with efficient and consistent functions to utilize the features of SoC platforms, including resource allocation and management, like the different cores, memories, and peripheral devices, configuration management, power and performance management, fault tolerance and redundancy management, sharing of resources using a common middleware library and services, and finally messaging services. Ultimately, we would like to facilitate deployment of applications for execution with different characteristics and resource needs. In other words, different computational needs, different mission criticality levels, timing criticality, and support different phases of the mission. Next, I would like to describe our middleware design concepts. These are the design principles that guide middleware development. Let me go over them. First, middleware supports fault tolerance by not using globally writable shared memory in any library or API implementations. Middleware provides options to secure the system state in process-restricted memory where it is supported by the host operating system. Middleware provides an inter-process messaging API so processes can exchange data in a safe way. On the next bullet, middleware supports determinism by not using locks in any of the library implementations, by providing a timing API to separate and synchronize application execution to specific intervals, by employing a single thread of execution for its runtime service, which we will discuss in a few slides. Other than the single thread, middleware will not create any additional threads of execution unless needed to support isolation. Finally, middleware supports performance by not using locks in the libraries and by supporting application parallelism in a multi-core deployment. We have the ability to pin process execution to a processor core. Now I'm going to give a brief overview of the middleware architecture. Like most modern software, we take a layered approach to provide well-defined interfaces. Going from the bottom up, we have the SoC hardware layer on the bottom, the system software layer, which consists of the operating system, hypervisor, bootloader, device drivers, so on, and then the middleware layer, which is what we're concerned with. Finally, at the top, we have the application software layer. In a nutshell, the middleware allows the user to allocate and manage the resources of a SoC system to dramatically trade computational performance, energy management, and fault tolerance objectives for a mission or application. The middleware allows a missions integration engineer to reason about the interactions between the applications and the system, and it allows them to create a set of configuration files to control this. This slide is a more detailed look at the layers. You can see the SoC resources here at the bottom of the slide in gray, followed again by the system software layer containing the operating system, drivers, and bootloader. Moving up, you can see the middleware layer. Note that the middleware consists of a couple of major components. a set of middleware service libraries, and a runtime component called the Middleware Service Application. I will get into a bit more detail of these on the next two slides. Finally, moving all the way up to the top, we have our application layer as usual. This is a list of our middleware service libraries. They provide the various services to the application through both direct calls and interaction with the middleware service application, our runtime component. In the interest of time, I'm not going to go into a great detail on each one of these services, but feel free to pause here or look for our presentations from the previous two flight software workshops. This slide lists the main functions of the runtime component, known as the Middleware Service Application, or MSA. The MSA provides runtime services to applications through a message interface. I'm going to read off these services because we haven't covered these much in the past. These services include deployment, hardware resource, power, communications, diagnostics, single SOC FDIR, which stands for Failure Detection, Isolation, and Recovery, or RESET, and multi-SOC FDIR. This slide shows the middleware service application architecture. This is the single thread of execution for the middleware that manages the protected runtime state of the middleware data. On the left, we have a set of middleware message queues for each application that interacts with the middleware. Messages are queued up by the application through our messaging service, and the MSA will service these queues to first check the message's validity, then it will dispatch the message to the correct event handler on the right. Note that the dispatch handlers will also have the opportunity to validate parameters and also check the request against a defined policy. This policy implementation is part of R4 and will be explained in just a bit. Before we get into the details of Middleware Release 4, this chart shows our release history. Hitting the highlights, we started the project in 2017 and have made several releases since then. We are nearing completion of our last planned release, which is the focus of this talk. Now let's get into the details of Middleware Release 4. So one of the goals we have in Middleware Release 4 is to complete the middleware service libraries. Some service libraries were updated to reflect the middleware design concepts that I described earlier. Some libraries could not be completed as originally defined because of the change in focus from the specific HPSC chiplet target to a more generic multi-core SOC target. Because of that, we weren't able to implement all of our requirements. You can see here the statistics. We had originally defined 196 requirements a few years ago. We've completed 119 of them. We have 34 new requirements to complete in Release 4, and we had to defer 39 requirements just due to the change in the hardware focus. And of course, we've identified 4 requirements that we decided don't really apply or make sense anymore. Now, I would like to take a look at the new service application features. The first of which is the Multi-SOC Failure Detection, Isolation, and Recovery, or FDIR. The objectives include accommodating multi-SOC topology, including N-modular redundancy, or NMR, for application deployment. To provide a coordination of fault management activities between multiple SOCs, for NMR applications, middleware will provide boot and load capability to support identical copies of the same application running on different SOCs, distribution of non-identical input to all application deployments using 2 rounds of exchange. This will be used to form a distributed consensus among multiple SOCs. Voting of output by a centralized entity. This will prevent having a single point of failure within the SOC network. And finally, the execution of a recovery action upon detection of a failure. So this is an illustration of that concept. In this diagram, we have 3 different SOC systems in gold and the fault monitor output voter in gray. The middleware services are used to perform the following timeline. At time 0, each SOC node collects its sensor data. At time 1, each SOC node broadcasts its local set of data to its peers. At time 2, each SOC node broadcasts the full set of data containing sensor data from all three sensors to its peers. At time 3, each SOC performs the computations on the full set of sensor data. Time 4, a command is sent from all peers to the output voter. And at time 5, the output voter sends the final command to the actuator. Some important things to note here. The SOC systems are the high performance, but maybe less reliable systems, hence the need for the redundancy. The fault monitor in this example, the output voter, is assumed to be a radiation-hardened, reliable component. Moving right along to additional features for the MSA, our middleware service application, we have hardware resource management. The objectives include to service requests from user applications for hardware resource info and access, to support exclusive access to hardware resources by user application, to arbitrate hardware resource access in a trusted execution environment. So just a little walkthrough of how this can work. The user would request a reservation of a hardware resource using a service application message queue. If the resource is available, it'll be assigned a unique key that's returned to the user. The user can wait for the resource to become available if they'd like to, using these application message queues in interaction with the MSA. But with the key, the user has exclusive access to the hardware resource until they release it. Earlier, when talking about the middleware service application, I mentioned the policy handlers. We are implementing policy handling as part of our Release 4. The objectives of this policy handler are to provide the capability to specify policy setting through a configuration file, to provide functions or an API for validating against policy specifications, to integrate with the middleware service application for policy setting and validation. So the requirements in a nutshell for this are that we want to provide the capability to establish policy for SOC devices, memory, power, performance, fault tolerance, and redundancy. The policy shall be specified in the configuration files for each middleware service application and implemented through the handlers for that service. The policy shall be validated at boot time and during program execution by the middleware service application. The policy specification and the configuration files include the resource that we are controlling. It is typically available in the device tree from the system software. We can have single or multiple instances of devices in a policy specification. Resource availability. Who is allowed to request this resource? Who, meaning an application here. How long will this resource be granted to the application? And finally, the type of resources, a single discrete resource or multiple resources. This slide highlights where the policy checks are implemented for each middleware service application hardware event handler. So you can see here on the right that it's specific to the unique handler and can be implemented as such. The middleware project was always intended as a research and development project, but as part of our final planned release, we are planning to take the first steps to raising the maturity of the middleware software. That work includes identify and document the requirements gap and technical debt for future implementation, conduct a documentation review and update for clarity and completeness, conduct design and code reviews on selected key modules and functions. Obviously, we can't cover all of the code in the time we have, and perform more in-depth system-level testing, stress testing, performance testing, etc. Finally, let me show you our Middleware Release 4 hardware environment. We have implemented the Multi-SOC hardware environment shown a few slides back. We use 3 Xilinx ZCU102 boards with independent Ethernet connections between them to represent the high-performance SOC nodes. The host computer is representing the reliable output voter. We would like to expand this to incorporate the high-speed serial rapid I/O devices, but we won't have the driver in time for Release 4, so we'll just stick with the Ethernet interfaces for now. And this is a picture of that environment. Note that each network cable is color-coded to show its dedicated connection to its peer. Let's move on to the last part of the presentation. I would like to talk about post-release 4 research that we are in the process of conducting. Feel free to email either myself or the JPL lead, John Lai, with suggestions about what you would like to see in future middleware releases or future direction of research, with the focus on high-performance spaceflight computing and flight software. We welcome your input. Given that, let's go over a few of the topics we've identified and we're looking at. So for the first research topic, we would like to take a look at how well the middleware integrates and operates with existing flight software frameworks, such as NASA's Core Flight System or JPL's F-Prime. As with any flight software system, there are often overlaps in functionality, exposing some incompatibilities. In the case of CFS is mostly thread-based, while middleware is focused on multi-core and protected processes. So there is a level of incompatibility there. The question here is, how well can we integrate existing flight software frameworks, and what approach should we take? Options include interface bridges and higher-level compatibility layers for the middleware. When we started middleware development, we were targeting the HPSC chiplet and the system software that was provided by the vendor. That included Linux for the high-performance multi-core subsystem and the RTEMS real-time OS for the real-time subsystem. For this research, we're taking a look at how middleware can adapt to different operating systems and real-time OS models, such as single-process, multi-threaded applications, which include the traditional RTOSes, such as RTEMS or, say, FreeRTOS, multi-process, multi-threaded applications like Linux, Greenhill's Integrity or VxWorks, space-partitioned or time-partitioned applications such as Integrity or VxWorks with its hypervisor, and partitioned safety-critical systems such as ARINC 653 systems. For this next topic, we would like to investigate the use of middleware on hypervisors. We have started this effort by running the Zen hypervisor on the Xilinx CC102 board, and we've been experimenting with both Linux and RTEMS guest operating systems on the hypervisor. Ideally, we would also like to try hypervisors like Integrity or the Wind River hypervisor. Closely related to hypervisors and operating systems is the topic of investigating the partitioning of computing resources, especially when it comes to mixed criticality. We would like to experiment with hosting critical applications and less critical high-performance applications on the same SoC system and demonstrating the ability of the hypervisor to isolate faults between the two subsystems. This effort would include some benchmarking activities to help determine the overhead of hypervisors compared to a regular operating system. The next topic is SMP and AMP. A high-performance multi-core system has a lot of possibilities for how software is deployed. Another possible variant is the use of symmetric multiprocessing versus asynchronous multiprocessing, or AMP. SMP is the default operational mode for middleware deployments on a multi-core system, but it would be good to investigate if we can use middleware in AMP mode as well, where there are separate operating systems running on different cores of the same SoC. In this scenario, we may want to reconfigure a system to accommodate different phases of the mission. For our next topic, we would like to take a look at how middleware will integrate in a heterogeneous environment, which is a combination of different types of compute platforms. In space applications, we're used to just working with your typical CPU. Now we're branching into multi-core CPU. Now in embedded computing, there's a number of other compute elements available, including things like GPUs, or graphics processing unit, TPU, which is an AI tensor processing unit, FPGAs, digital signal processors, and so on. So for this topic, we'd like to investigate how we can use these different compute elements, such as GPUs, TPUs, FPGAs, with the middleware, and investigate how that fits in with our fault detection and isolation. For this topic, we're planning on taking a look at a couple of different low-cost development boards including an NVIDIA Nano development board, which has a GPU, and it can do things like image detection and recognition, and this Google Coral AI development board, which has an onboard TPU accelerator. One of our last research topics is to investigate how middleware might integrate in a secure computing environment. So we want to look at the role and functionality of middleware in the secured execution environment. We want to look at how middleware would fit in with the secure boot process. Look at the potential, we want to look at data encryption and authentication. And finally, how does middleware interact or help us manage private and public keys? Middleware was originally targeted for the high-performance spaceflight computing chiplet, or HPSC chiplet. And as I've described in this presentation, we've moved the target of middleware to a more generic high-performance multi-core SoC system. But we would also like to look at how middleware can apply to some of the upcoming high-performance computing systems, such as the BAE Systems RAD 5545 multi-core computer, some of the upcoming multi-core RISC-V systems, such as the Geissler Noel 5, and of course Geissler's upcoming multi-core Leon 5, and of course we're going to keep our eye on the target of future HPSC architectures as they evolve and are released. So this concludes my brief overview of HPSC middleware, our Middleware Release 4, and some of our post-R4 release topics. Feel free to contact either myself or John Lai at the email addresses shown earlier in the presentation if you would like to provide any additional input on research topics that you're interested in and how HPSC middleware might help you adapt to future flight computing architectures.